Okay, what we should know about springs already is that a spring, and let me put that there, a spring has a certain equilibrium length, and if I stretch it from that equilibrium length, it requires a certain amount of force. We really talk about the force that the spring puts on an object. So if I'm trying to hold that there, the spring force is going to be proportional to the displacement, how far I've stretched the spring. Okay, and we really talk about the magnitude, the size of that force is equal to some constant times that displacement. And that constant is called, appropriately, the spring constant. And that's true whether we stretch it or compress it. In other words, if we compress that spring, it's going to put a force back on us proportional to the displacement. And I'm not going to worry about the directions. You can tell the directions just by the context. In AP, we make those as vectors, and we give one of them a negative sign. The spring constant, by the way, newtons divided by meters, newtons per meter. So that's something that you should have learned in the previous lesson. So now, let's look at stored energy. Okay, clearly, if I stretch that thing out there, there's a certain amount of energy. If I let it go, it's going to move. That'll be converted into kinetic energy. So we say that springs have an elastic or spring potential energy. And by the way, the spring constant is kind of an indication of how stiff that spring is, how hard it is to stretch it, how many newtons it takes to stretch it each meter. So this spring potential energy is going to have a K in it. It's going to have a spring constant. A bigger spring, all things being equal, is going to have a bigger stored energy when you stretch it. It's definitely going to have to do with the delta x. It turns out that it has to do with delta x squared, and that there's a 1/2 in there. If we figure out the total work done by the spring as it pulls back in, it ends up being this amount. That's how much energy is stored in there. That means when we're doing energy problems, we don't have to worry about this spring force, okay? That's where a lot of people get into trouble. They do work equals F delta x cosine theta, and they plug that in for the F. But look, that force is changing the entire time. It's not a constant force, so you gotta be really, really careful when you do work done by a spring. It's not as straightforward as people think. This is an easier way. If we're talking about work or energy, use this. Okay, let's look at that. If let's use this exact same spring, okay, and I compress that spring to this distance, delta x, and I put a ball there, and I hold it, okay? Think of a pinball. When you pull that thing back, it pulls the spring back and the ball's on there. So at rest, and let's say there's a spring constant K of 20 newtons per meter. The mass of the ball is 0.2 kilograms. And I'm going to say that I compress it let's say 0.1 meters. Okay. This is a different thing when we talked about, conservation of energy with gravitational and so forth. There were different energies at different locations. Here, it's a different situation that looks different. Okay, that spring is compressed. So let's see what happens here. I pull that thing back and I put the ball there. Well, here in this picture, the kinetic energy is 1/2 mv squared, 1/2 times 0.2 times 0 squared, because it's at rest, equals 0 joules. The potential energy, spring potential energy, and I'm not going to have this going up and down right here. That gets a little complicated, is going to be 1/2 times K times X, or delta X squared. And you'll see that written a couple different times, different ways. Okay, that's 10 times 0.01. It ends up being 0.1 joules, just a coincidence. So my total energy there is 0.1 joules of the system. And the system now includes the spring. Okay, now I let it go. And I want to find out how fast it's going when it gets back to equilibrium. Here's my equilibrium line. When it gets back to equilibrium, how fast will that ball leave? Okay, so I know no net outside work done by any forces. Nothing's pushing, pulling it. I've stopped. I've let go of it, right? So that means all the way while this is stretching out, the energy is conserved, but potential energy is decreasing, kinetic increasing until we get to there. And there, the kinetic energy is 1/2 mv squared, 1/2 times 0.2 times v squared. That's what we're looking for. The potential energy, spring potential energy, is 1/2 times K times X. It's not compressed. This is how much it's compressed or stretched. It's back to its normal length. So that's 0 joules. The total energy, therefore, well, I shouldn't say therefore, the total energy we know from before is 0.1 joules. So 0.1 minus 0 is 0.1. And when we solve that, look at that. 1/2 times 0.2 equals, that's 0.1 times v squared equals 0.1. V equals 1 meter per second. Okay, the same thing would happen in reverse. If I said I throw a ball at 1 meter per second at a spring with spring constant 20, what would happen is it would come in here and it would make that spring compress. And at its maximum compression, before it starts going back in the other direction, it would have a velocity of 0. So it would this would be the exact same if I had the ball going in the other direction. So it had a kinetic energy of 0.1 joules. Sorry, that's supposed to be a J. No potential energy at the beginning because the spring's not compressed. Total is 0.1. Total when it compresses to the point where it stopped moving in. So when we say, how far will it go? We're saying when that spring is as compressed as far as it'll go, and the kinetic energy is 0. So we've just done two things. One is starting at rest, shooting something out. The other is shooting something, having something come at it and making it compress. And it's basically the same problem. Here, in this case, all kinetic, no potential. Here, all potential, no kinetic. But there is also in-between cases. Okay, so let's say we started with this, and let me draw my equilibrium line down here. Now, I've let it go, but it hasn't gone all the way. It's about here. And I want to find how far it is when the velocity of the ball is 0.5 meters per second. I want to find out what the displacement is, that delta x. Okay, it's not as big. It's not compressed all the way. That was back here. It's somewhere. I've let it go and it's moving, but it's not all the way out. So we do that same thing. Kinetic energy is 1/2 times 0.2. That ends up being 0.1 times 0.5 squared. That ends up being 0.25, 0.025 joules. So that's the kinetic energy when it's going 0.5 meters per second. Again, it's the kinetic energy of that ball. The spring, we're not worried about the kinetic energy of the spring. It's hard to measure that. Potential energy of the spring, well, I know the total has to be 0.1. 0.1 minus 0.025. This is going to be 1/2 times K times x squared equals 0.1 minus 0.025 is 0.075 joules. And when we take that and we solve that, we get square root of 0.0075 because we divided by 1/2 times 20, and we get x is 0.0866. meters. That's my displacement. That's how far the spring is still away from equilibrium. Okay, what's important here? Conservation of energy. Draw it, redraw it. Okay, there is no change in gravitational potential energy, and we're only going to be giving you horizontal problems for now. Okay, another situation that could be like this is a bow and arrow. Okay, you have the bow acts like a spring. Okay, so you've got a certain delta x. If this is the relaxed position, that's your delta x. And we still have a 1/2 kx squared. Starts from rest at the end. And again, it's kind of important to redraw these things each time. Here's the bow and arrow after the arrow, after it's been released and the arrow is moving. A lot of v, delta x is 0. Back here, a lot of delta x, v is 0. And we could ask for any time in the middle. If I gave you a delta x, you could calculate the v. If I gave you a v, you could calculate the delta x.